What's up, everybody, and welcome back to another video on ACT Math. This is part 3 of 4 for ACT Critical Math Concepts on ratios, percents, data analysis, and probability. So we're going to start off with ratios, rates, and proportions. And first, I want to talk about what is a ratio. So a ratio can be expressed like a fraction, but it can also be expressed with this colon. And these are essentially equivalent. So 1/2 can be written as 1 to 2. Likewise, 4/9 could be written as 4 to 9, etc. 2/5 can be rewritten as 2 to 5. And notice that order. The numerator is generally that first number and the denominator is that second number. For a final example, we have 3/7 likewise, which can be written as 3 to 7. So again, these are just different forms of representing the same thing. Now, sometimes on the ACT, you might get a question like, what is the ratio of A to B? And if it's originally presented in an equation like this, you might be like, okay, well, A to B, it's 3A to 7B, so it's a ratio of 3 to 7. But you don't want to solve it that way. Here's how you want to do it. Remembering that the ratio of A to B is the same as saying, what is A over B? So we're just going to solve using standard variable isolation. So check this out. First, I'm going to divide both sides by 3. That's going to knock those guys out. And now I have A equals 7B over 3. Then I'm going to divide both sides by B like so, cross those guys out, and then I have A over B equals 7/3. So the ratio of A to B is in fact the reverse. It's 7 to 3. Now let's talk about rates, and specifically when we're talking about rate problems, there's a very simple but a very powerful formula that you want to remember, which is distance equals rate times time. So of course, D represents distance, R represents rate, and T represents time. So now let's take an example problem and see how it works with the distance equals rate times time formula. Laura can swim 2 laps in the local swimming pool every 1.5 minutes. At this rate, how many minutes does Laura need to swim 12 laps? So check this out. In this case, the distance being swam is 2. That's 2 laps. And the time in which it's happening is 1.5 minutes. And we're trying to find out the rate. That's the unknown. So I'm going to leave that in here like so. So R times 1.5 equals 2. So to solve for the rate, now I can divide by 1.5, divide by 1.5, boom. 2 over 1.5 can also be represented as, if I multiply top and bottom by 2, as 4 over 3. So Laura's rate is 4/3, meaning she can swim 4/3 laps in a minute. Now that I know my rate, I can plug it back into distance equals rate times time to solve for this 12 laps, right? So check this out. To swim a distance of 12 laps with a rate of 4/3, what is the time? And now to solve this, again, is variable isolation. To get rid of the 4/3, I multiply both sides by 3/4, multiply both sides by 3/4, boom, boom, cancel, cancel. 3/4 times 12, or 3/4 of 12, is 9. So it would take 9 minutes to swim 12 laps. Next, we're going to talk about proportions. And again, proportions are another way to solve these types of problems, and it's really, really effective. I love proportions. So check this out. Let's say we're given a preset proportion, A over B equals C over D. So there's something really cool that you can do with proportions usually to solve, which is called cross multiplication. So check it out. The C comes down and multiplies the B, and the A jumps down to the other side of the equal sign and multiplies the D. And when you execute this cross multiplication, you get BC, see how it's BC on the left, and AD on the right. Now again, that's arbitrary. I could have put BC on the right and AD on the left. It's all good either way, because that equal sign, it doesn't matter what is on each side. So to put this into practice, if I said that 1/3 equals X over 9, to solve, once again, I'm going to cross multiply. So that X is going to jump down and multiply the 3, the 1's going to jump down and multiply the 9, and we get 3x equals 1 times 9. This simplifies to 3x equals 9. To solve, we divide both sides by 3 and get x equals 3. Now I'm going to show you how to use proportions in a word problem. So for example here, if 7 pounds of plums makes 8 fruit rolls, how many pounds is needed to make 20 fruit rolls? So check this out. I'm going to start when I set up a proportion with these labels. Now, again, this is arbitrary. That's the beauty of it. But I'm choosing to designate the top portion with my plums value and my bottom portion with rolls value. I could also flip that, but I'm going to choose it and I'm going to stick with it. So then here's kind of the scaffolding, right? So I know I'm going to have a fraction equal a fraction. So how do I designate what goes where? So check it out. It said 7 pounds of plums makes 8 fruit rolls. That's the relationship. So I'm going to throw 7 on top in the plum section and 8 on the bottom in the fruit roll section, okay? And then the question is, how many pounds is needed to make 20 fruit rolls. So I know 20 is going to go on the bottom on the right side, and X, that's representing my unknown because it's saying how many pounds of plums is needed, so that X is going on the top. Once we have the proportion set up, this is no problem. We just cross multiply like so, right? So 8 is going to multiply the X, 8X, and on the other side, 7 times 20, which is 140. And then to solve, all I got to do is divide both sides by 8, standard variable isolation. Boom, cancel those out. 140 divided by 8 is 17.5 or 17.5. Here's another quick example. To make 4 batches of cupcakes requires 7 tablespoons of sugar. How many tablespoons is required for 5 batches? So check this out. I've chosen to put batches on top, tablespoons on the bottom. Again, arbitrary, but let's roll with this. Set up the scaffolding, and now 4 is going to go on the top in batches, and that corresponding 7 on the bottom with tablespoons. And then over here, we've got 5 batches. Of course, 5 goes on top, and the unknown is the tablespoons on the bottom. Cross multiply like so. 5 times 7 is 35. 4 times X is 4X. Last but not least, we divide both sides by 4. Cancel those guys out. 35 divided by 4 is, of course, 8.75. Boom, done. Now let's talk about percent. So what is a percent? So first I want to go back to what my French teacher always used to say back in the day. Percent is a French word. It's per cent. Cent is a French word. It means 100. So when we're talking about percent, when we say 9%, we really mean 9 out of 100, okay? So every percent is really that number out of 100 in fraction form, which means that this also in decimal form is 900ths or 0.09. So you take another example, 73% is 73 out of 100, which is the same as 0.73. Likewise, we have 16%. That's, again, 16 out of 100, or 0.16. And finally, 125%, same deal, 125 out of 100, and that's 1.25. And you notice an interesting trend, which we're going to talk about more in a second, but that decimal equivalent of every percent is the same thing. You just move the decimal 2 spots to the left. Now we're going to talk about the percent equation. This is an amazing equation when it comes to percent problems, so check it out. It's the percent times the total equals the part. But of course, that percent is in decimal format. I'm going to show you what that means in a second. So if you get a question that is, what is 12% of 50? Notice the color coding. So that 12% is going into the equation. But again, it's not going in as 12. It's going in as the decimal equivalent. To get that decimal equivalent, we just move that decimal 2 spots to the left. So that is 0.12. Then we know that the total, they're saying of 50. A lot of times the word of is going to precede that total, right? So we're taking 12% of 50. So that goes in the next spot. And then we're trying to get the part. 0.12 times 50, if you multiply that out, gives us 6. 6 for the win, done. Now we're going to talk about a question where it's worded slightly differently. It's going to say 9 is what percent of 45? So guess what? Now we're solving for the percentage. We don't know the percentage, right? So I'm going to plug and chug as follows. So X is my percent. I don't know what it is. My 45 is the total, because again, you see how it follows that word of. And of course, 9 is my part, so that's going to go on the right-hand side. And so now we have the percent equation. We just use variable isolation. So we divide both sides by 45, boom, boom, and we get X equals 0.2. But we want it as percent form, right? So again, to convert that decimal equivalent, we just pop the decimal place 2 spots to the right. So when we go percent to decimal, we go 2 to the left. Decimal to percent, 2 to the right. So the answer is 20%, done. Now we're going to go through one more example. 30 is 75% of what number? So check it out. We now have the part, we have the percent. We're actually trying to find the total now. So we're going to set it up the same way. So 0.75, again, that's my decimal equivalent of 75%, times what total? We don't know. We're going to try and figure that out. So that's our X equals our part, which is 30. Same deal, we divide by 0.75, variable isolation, get rid of that 0.75. So 30 divided by 0.75 is, of course, 40 for the win, done. Other types of percentage problems could be percentage increase. So I'm going to show you how these work as well. So let's say we have a starting value and we're asked to find what is a 20% increase. So check it out. This is the fastest way to do it. Since we're talking about increase, I'm going to add this value to 100. So it's really 120% of 1200. That's what we're talking about. So now I just got to take 120% of 1200. So to do that, first I convert it to its decimal equivalent by popping the decimal place 2 spots to the left, boom, boom. So now it's 1.2 times that original value of 1200. So 1.2 times 1200 is, of course, 1440 for the win. Done. Likewise, if we have a percentage decrease, it's very much the same process, except we're going to be subtracting. So let me show you what that looks like. So let's say, again, we got that starting value of 1200, but now we're talking about a 35% decrease. So before, we took 100 and added the increase, added the 20, but now it's a decrease. So we take 100 and we subtract 35, meaning a 35% decrease is equivalent to taking 65% of the original. So once again, I'm going to move that decimal 2 spots to the left, take 0.65 and multiply it by 1200. This, of course, gives us 780. Next, we're going to be talking about units and in particular conversion ratio. So for example, let's say we have to convert 2 miles to feet. And this is also called dimensional analysis. So we can take our 2 miles, and I'm just throwing it over 1 because we can put anything over 1. And I say, well, I want to get 2 miles into feet. Well, what is the relationship of miles to feet? Well, I know that 5,280 feet is equivalent to 1 mile. So why did I put it this way? Why didn't I put miles on top of feet? Is because you want the units to cancel out. Like, we want the miles to be gone so that feet remain, because we're trying to convert this to feet. So when we set it up this way, check it out. The miles on top and bottom, boom, they just cancel out. Then we multiply across. 2 times 5,280 is 10,560 feet. Done. Now let's say we want to do a bigger conversion, like 3 days to minutes. So check this out. This is going to be involving multiple conversion ratios. So we start with 3 days, and first I'm going to convert it to hours because that's a little easier, right? So I know that there's 24 hours in 1 day. So that's cool. Now we've got a conversion ratio to take us from days to hours. So we can now cancel out those days. Boom, now we're in hours. Now I need to go from hours to minutes. So what's the equivalency between hours and minutes? Well, I know we've got 60 minutes to 1 hour. And again, I recognize those are plural, but I'm just trying to have all the units be identical, right? Hours, hours, days, days. Now, since we have hours on the top and bottom, I can cancel those out. Boom. Now we're done. Now we've got the value set up. We just multiply across. 3 times 24 times 60. Of course, in the denominator, we just have 1. So that gives us 4,320 minutes. Now let's talk about scatter plots, and in particular lines of best fit. So what is a scatter plot? A scatter plot is a collection of data. So this could be about anything, right? I've just taken a standard XY coordinate plane and I've put down a bunch of data points. Those are those points. So for example, if you're measuring how many times people go to an ATM per year, if you're measuring how often do you order fast food per year, right? Like, these could be actual data points of those values just plotted on here. So that's what a scatter plot is. Now, when we talk about a line of best fit, a lot of questions will ask about a line of best fit. What is that? It's basically trying to predict the pattern in this scatter plot. So if we said, for example, this is the amount of times you go to the ATM based on how far you live from a city in miles or something. So you can see, like, hey, if you're 1 mile away, you maybe go twice a year. 2 miles away, a little bit more. And then for people that live really far away, you'd go 10.5 times a year. So with the scatter plot, what we're trying to do with the line of best fit is basically make a generalization, make a prediction about the trajectory and the general trend in this data. So for example, and I always think about it as threading the needle. We try to thread the needle through the points, try and get it in the center as much as possible. And now we have a line of best fit, which is a great predictor. So if somebody comes along and says, hey, we know that their X value is going to be 6, what's their Y value likely going to be? Well, I can use my line of best fit and be like, it's going to be about 6.8, 6.7, something like that. And remember, there's a lot of times on the ACT where they're going to ask you about one of these scatter plots and lines of best fit. And they might be like, hey, what would be the predicted value if the X value is 8? And you may be like, oh, cool, I see a point here. That's probably more accurate because that's real data. So I'm going to choose 8, right? But really, in these questions, you want to be careful about the wording because usually they're going to be referencing the line of best fit, not the actual data point. So the answer instead would be like 8.7, 8.8, something like that. Now let's talk a little bit about understanding graphs in general when you see them on the ACT. So first of all, when they're talking about slope, what is slope? Slope is, again, rise over run, and there's certain terms that we want to be familiar with. For example, positive slope, also called increasing slope, is where the graph is going up from left to right. So for example, in this graph, it's this portion right here. It's actually more than this portion, but that is an example of positive slope. We can also have negative slope, which is also called where the function is decreasing. That's when it's going down from left to right, which could be like this portion, for example. That's a portion of the graph where the slope is negative. We generally, on a graph, will have a y-intercept. That's quite literally where the graph intersects the y-axis. And for practical terms, this is the initial value. It's basically the value at either time 0 or value 0 or whatnot. So when they're talking about initial value, you want to think y-intercept. And there we can see that y-intercept is that green value on the graph. Next, we have our x-intercept. This is where it hits the x-axis. And this is what we would consider the point of no value. So what I mean by that is in some questions, like for example here, this could be talking about revenue at a company. So the x-intercept would be the point at which the company is earning a revenue of $0. And that is, of course, this purple point right here on the graph. Finally, when we talk about quadratics in particular, okay, we have a vertex. So a vertex is going to represent the min or max value. Now, of course, in this graph, since it's going down, it's going to be a max value. But if it was an upward-facing parabola, the vertex would be the minimum point. So the vertex, of course, is that point right there. It's the highest point on the graph. Now let's talk about reading tables and specifically data in tables. So let's say we take this example here. We've got male, female, and we're looking at the number of males taking math and science, females taking math and science. Now, a question can say, what fraction of students surveyed take math? So in a question like this, when we're talking about a fraction, it's very straightforward because we're looking at whatever is the total amount of students. So what is the total amount of students? So I'm taking the total values of 70 and 130, because that's a total in each category. So that gives us a total of 200. And where am I pulling that 70 from? That 70 is the total amount of students that just take math. So quite literally, the fraction is 70 over 200. Boom, done. Now we're going to take the same table and we're going to ask a more specific question. And this is very important because with this limiting language, you want to understand exactly how to limit your total value. Now we're going to look at a different type of question from the same data set. So it says, of the female surveyed, what fraction of students take science? So that limiting language is very important. When they say of the female surveyed, we are immediately down specifically to females. So I'm highlighting the female section because we don't even want to mess with the data in the other two rows. So we calculate our total from those females, right? The 46 plus 58. And then what fraction takes science? Well, it's the amount of females that take science, not the total that takes science, just females. So it's 58 out of that total of 104. Boom, done. Now we're going to go with one more example of that limiting language. Of the students who like math, what fraction of students surveyed are male? So when they're talking about math, now we're limiting to just this column, right? Of the students who like math, what fraction are male? So we take the male value of 24 in the math section out of the total of the math section, which is 70. Boom, done. Now let's talk about center, spread, and shape of distribution. So check this out. If we have a data set, 1, 2, 3, 3, 3, 4, 4, 5, 7, 7, 8, 9, 9, I want to look at the critical values. So what am I talking about? I'm talking about mean, median, mode, and range. So what are all of these terms and what do they represent? So check it out. First, let's talk about mean. So when we talk about mean, it's really a synonym for average. So how do we take the average of a data set? We take all the values in the data set, we add them up, and we divide by the number of values that there are. So if you count these up, there are 13 values. So we add them all up, we divide by 13, and of course we get a mean of 5. Now let's talk about mode. So mode you can see is in green, those 3's are in green. Why? What is mode? Mode is the value that you see the most of. So I see 2 7s, I see 2 4s, I see 2 9s, but I see 3 3s. So since we have 3 3s, we have the most of 3s, our mode is 3. And by the way, it is possible for a data set to have multiple modes. This one does not. This has one single mode, but it can happen. Next, let's talk about the median. The median is the middle value of the data set. So again, you have to arrange the values from least to greatest, and then you can quickly identify the median. In this case, that 4 is the middle value, right? Now, you can also have cases where you have an even number of terms, so there's not a distinguishable middle value. If, for example, we removed this term, now we'd have only 12 values. So what would you do in this case? Well, you would take the 2 middle values in this case, right? So we now have 12 terms, so it's the 5th and the 6th that would sort of both contribute to the median value. And then you would take the average of these guys. So you would take 4 plus 4 divided by 2. Of course, that happens to still be 4, but that's the process. Finally, let's talk about range. So range is the difference of the greatest and least value. It's literally the distance between them. So check this out. Here, the range is going to be the biggest value, 9, minus the smallest value, 1, which gives us a range of 8. Boom, done. Now we're going to talk about standard deviation. So check it out. What is standard deviation? It is the measure of the spread of data. Now you're not going to have to calculate it. So I'm not going to give you the formula to calculate standard deviation, but you do want to be familiar with what it is in general sense. So check it out. I'm going to give you 2 examples of a larger standard deviation and a smaller standard deviation. So let's say we have these values, 5, 5, 6, 6, 7, 7, 8, 8, 9, 9. And then here's another example, 6s and 7s. So you can see on the set in the right, it's more tightly packed. There's just a window of 6 to 7, and so there's not a lot of spread in the data. Versus here, it's not that spread out, but it's more spread out, right? Because we go all the way from 5 to 9, the data is sort of more evenly spread. So if we look at it on a graph, this is what it looks like. You see that nice distribution spread out, so that's what we call a larger standard deviation. Conversely, with the smaller one, see, it's all tightly packed together. Those 2 bars consist of all the data. So that is, in a rough sense, what standard deviation is. Now we're going to talk about box and whisker plots. So what is a box and whisker plot? So check it out. A box and whisker plot literally looks like this, a box with little whiskers pointing out. So what does it represent? So check this out. This tail end on the left represents the minimum value of the data set. So you can see in this example, the minimum value would be 2. This side on the right represents the maximum value. So here, the max value would be 10. Then there's usually a line down the center, somewhere in that box. It doesn't have to be exactly in the center. In this case, it is. That value straight up represents the median of the data set, which is again the middle, so that's 6. Next, we have this left side of the box that represents the lower quartile. So that's like the 25th percentile. In this case, the lower quartile would be 4. And then on this right side, that green section, the right side of the box, that is the upper quartile, the 75th percentile. And in this example, that would be 8. Finally, we have the IQR. That is the interquartile range. That is the upper quartile minus the lower quartile, which in this case is 4. Boom, done. Next, we're going to talk about stem and leaf plots. So this is, again, another way to represent data. I'm going to show you how to use a stem and leaf plot with this specific example. So let's say we've got all these various heights of plants laid out. So it's tons of data. Again, a stem and leaf plot is just a neater and a more organized way to represent the data. Now, why is it called a stem and leaf plot? It's because it has stems and leaves. And usually the stems represent the value in the tens place and the leaves represent the values in the ones place. So for example, I have stems of 0, 1, 2, 3, 4, 5, and that represents 0, 10, 20, 30, 40, 50. Now I can organize the data in a different way. It's just going to be easier to read. So everything without any tens, the red values are going to go on top. Anything with a 1 in front with a single 10, like 13, 15, 19, those go with the 1. And so on and so forth. So again, it's just another way to lay the data out. And it's good to understand how to read and interpret a stem and leaf plot as well. Now I'm going to show you another example to generate a 2-way stem and leaf plot. So check this out. Let's say we have 2 groups that we're comparing side by side. So when you generate a stem and leaf plot from this data, it's going to look like this. So in this case, the stems are in the middle and we have leaves on either side. So we have our 0, 1, 2, 3, 4, 5 again. And likewise, you can see the red values of class 1 are going to slide into those appropriate slots, right? That 4, 4, 3 really represents 14, 14, and 13. The 5, 5, 5, 5 represents all of those 25 values, etc. And for class 2, we place it in like so. And again, it's the same organizational structure. Another thing we want to be familiar with is data collection and conclusions from that data collection. So when we talk about data collection, there are a few different methods that we want to be familiar with. So first, we have an observational study. So what is an observational study? It's where you observe subjects and record data based on an existing factor, usually with no interference. So you can think about, for example, if you'd watch wildlife and you just want to watch them, you're not experimenting or changing anything. Then you have what's called a controlled experiment. A controlled experiment is you test a single variable using 2 groups. So it could be, for example, you want to test the effectiveness of a particular suntan lotion. So one group, you might give them nothing, and the other group, you give them the suntan lotion, and you see how their skin reacts to sunlight exposure. In that example that I just gave, you have a control and an experimental group. Obviously, the experimental group is where you're giving them the new factor, that suntan lotion, and the control group is where you're leaving everything as is. And then you can compare the two groups to see what the impact of the suntan lotion is. Finally, we have a survey, and in a survey, you're just going to gather data via questionnaires. You're going to ask people, hey, can you answer this? Can you rate this on a scale of 1 to 10, so on and so forth. Now we're going to talk about probability. So what is the definition of probability? Probability, very simply, is the number of ways to win divided by or over the total number of possible outcomes. So what does that mean? Let's say you're playing a lottery and there's 10,000 possible combinations of numbers you can choose, but only one that can win. So you would say your odds in winning that particular lottery would be 1 out of a total of 10,000. Now let's take a more concrete example. What is the probability of rolling an even number on a dice? So check this out. We have a dice, we have 6 possible options, 1, 2, 3, 4, 5, 6. Even numbers would be 2, 4, and 6. So when we're generating the probability, we know that since there's a total number of 6 outcomes and 3 of those are even, we have a probability of 3 out of 6. And of course, it's a fraction, so we can reduce that to 1/2, boom, done. Now let's take a different example where it says, what is the probability of rolling a 2 or 5 on a dice? So now we got 2 options. When you see that or word, really what you're doing is you're calculating the probability of each of those individual events and then adding them together. So check this out. What is my probability of rolling a 2 or a 5? So 2 and 5, we've got 2 ways to win. We can either hit a 2 or a 5. So again, 6 options total, 6 outcomes total, and we got 2 ways to win. That of course is 2, 6, which reduces to 1/3, done. Now let's talk about joint probability. Joint probability is where we're taking the probability of something and something else happening. Usually when we talk about joint probability, the event probability of this happening and this happening is usually going to be lower than the probability of each individual event happening. Take the example of winning a basketball game. It's pretty obvious that it's less likely to win 2 games in a row than it is to just win 1 game. So when you stack on what's the probability of winning this game and the next, it's going to be lower than just winning that next single game. So here's an example. What is the probability of rolling an even number and then a 5 on 2 consecutive rolls? So it's even and then a 5. So again, we've got 6 outcomes. So we're going to take the probability of that first event. So that's rolling an even number. So we got 3 ways to win out of 6. Then we got to take the probability of rolling a 5. So probability of rolling a 5, there's just one way to get that 5. That's 1/6. So those are my 2 probabilities. And then the probability of both this one and that one occurring, we take these and we multiply them. That's joint probability. We multiply. So 3/6 times 1/6 is 3/36. And of course, we can reduce by dividing both by 3, top and bottom, and we get 1/12 for the win. Next, let's talk about expected value, which is definitely tested on the ACT as well. So expected value is a way to calculate your expected return when you play a particular game. And I want to show you what expected value is with an example. So what is the expected value of playing the following game given the probabilities of each event and the corresponding prizes? So check this out. Let's say you can have 5 different events, A, B, C, D, and E. You can even imagine it on some sort of like drawing out of a hat or something like that, and then each event will happen as a result. And the probabilities are listed there alongside the prizes. So there is a 0.2 or 20% chance of event A being selected. There's a 25% chance of event D being selected, so on and so forth. So to calculate expected value, what we do is we take that probability value with each prize and we multiply them. We multiply, and then we add all of those products. So check it out. See, it's 0.2 times the corresponding 8, 0.3 times the corresponding 4, so on and so forth. We add all of these up and we get $15.30. So what that basically means is for somebody who's playing this game, for every time they play, the expected value is $15.30. Next, we're going to talk about the counting principle. The counting principle is a way to count all the various combinations you can make with different items. And really the best way to explain it is with an example. So let's say we have 7 pairs of socks, 3 shirts, and 9 pairs of pants. How many unique outfits can you make with 1 shirt, 1 pair of pants, and 1 pair of socks? So this is actually a pretty straightforward process. If I have 7 socks, 3 shirts, and 9 pairs of pants, to get the total number of outfits, I take all those values and I multiply them. 7 times 3 times 9, which is of course 189, boom, done. Next, we're going to talk about permutations. Permutations is all of the number of ways that you can order a set of items. So this is when order matters. And again, it's going to make more sense if I explain what permutations are with an example. One common example of a permutation are passcodes, like 4-digit passcodes. Those are permutations because 1, 2, 3, 4 is different than 4, 3, 2, 1. It's the same number, but the different ordering changes the actual passcode. Now, this formula here is how to calculate the number of possible permutations giving a set of information. So this is n factorial over n minus r factorial. And I'm going to explain what n and r are in a second, but what is factorial? Factorial is what I call the multiplication countdown. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1, etc. So n is the total. So when I say total, it's the total amount of things that you're arranging. And r is the amount that you're choosing. So for example, if you have 10 people and you're trying to arrange 5 of them in an order, your n value would be 10, your r value would be 5. So now let's take an example. If 5 horses A, B, C, D, and E are in a race, what are all of the possible arrangements for the top 3 positions? So you can see they're color-coded. 5 is, of course, your n value. 3 is your r value. So if we plug and chug into our equation, it's 5 factorial over 5 minus 3 factorial. So now I'm going to show you what this looks like when we multiply it out. 5 factorial, again, is 5 times 4 times 3 times 2 times 1. Since 5 minus 3 is 2, the bottom is going to be 2 factorial, or 2 times 1. Then we multiply it across. We get 120 over 2, which simplifies to 60. So in this case, there would be 60 possible arrangements for the top 3 horses. Finally, we have combinations. So combinations are similar to permutations. We're trying to figure out all the variations we can have when we have a set number of things and we're choosing a subset of that set number. But in this case, order does not matter. So what is an example of when order doesn't matter? So for example, you could think like, okay, when you're ordering a pizza and you have a number of toppings, we don't think about the ordering per se, but we're talking about the grouping. So I can get pepperoni and mushroom. I can get onions, pepperoni, and mushroom. I could get green peppers and pepperoni. So these are all different combinations. So this formula is very similar. It's the same as the permutation formula, except it's got an extra r factorial on the bottom. And once again, n represents our total, and r represents the number of items we're choosing. So here's our example. If there are 7 pizza toppings available, how many unique pizzas can you make if you're allowed to order 4 toppings? So again, 7 total options. We're choosing 4. So we plug and chug into our formula, 7 factorial over 7 minus 4 factorial times 4 factorial. So again, that 7 minus 4 is going to be 3. On top, we got the multiplication countdown, 7 times 6 times 5 times 4 times 3 times 2 times 1. On the bottom, we've got 3 times 2 times 1. 4 times 3 times 2 times 1. So just so you can see what goes where, you can see that 7 factorial corresponds to that top level. The 7 minus 4 factorial are those first 3 numbers right there. And last but not least, that 4 factorial corresponds with the 4, 3, 2, 1. When we multiply it out, we get 35 for the win. That's it for this video on ratios, percents, data analysis, and probability. I hope you enjoyed this video, and if you did, please click that like button. And if you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.